There's a place at the edge of everything we know, a line so far from Earth that light itself takes over 16 hours just to cross it. For decades, the world's most brilliant scientific minds drew maps of this boundary. They ran their equations, built their models, and arrived at confident conclusions about what existed out there at the very frontier of our solar system. They were wrong, not slightly wrong, not approximately wrong, catastrophically, fundamentally, disturbingly wrong. And the only reason we know that today is because a 47-year-old spacecraft, built with technology less powerful than your pocket calculator, crossed that boundary and sent back data that shattered everything. There's a silence that exists beyond the reach of the sun, a cold, ancient silence that has never been touched by sunlight, never been warmed by solar wind, never been mapped by human instruments. For most of human history, we didn't even know this silence existed. We assumed that space was space, empty, uniform, infinite, and indifferent. We were wrong about that too. When NASA launched Voyager 2 on August 20th, 1977, the mission had a simple, elegant ambition: tour the outer planets, fly past Jupiter, swing by Saturn, use gravity to slingshot toward Uranus and Neptune, collect photographs, return data. That was it. The mission was supposed to last roughly 4 years. Nobody in that room at JPL, nobody signing the funding documents, nobody staring at the launch footage through tear-streaked eyes genuinely believed this machine would still be operating nearly 5 decades later. Nobody planned for what it would eventually find. And yet, here we are in the year 2026, still receiving signals from Voyager 2, signals that travel for over 16.5 hours at the speed of light just to reach our antennas. And those signals are telling us things that are rewriting the foundational chapters of astrophysics. But here's where it gets complicated. The story of what Voyager 2 crossed is not just a story about a boundary. It's a story about a boundary that scientists insisted for decades had specific and predictable characteristics. They had equations for it. They had models. They had consensus. And every single one of those confident, peer-reviewed, institutionally endorsed predictions turned out to be wrong in ways that nobody fully anticipated, and nobody has fully explained to this day. Think about what that means. We are talking about the collective intellectual output of the greatest space agencies on Earth, armed with supercomputers, decades of observational data, and the most sophisticated theoretical frameworks physics has ever produced. And a machine launched in 1977, running on technology that makes your current smartphone look like a supercomputer by comparison, flew to the edge of the solar system and proved them wrong. That is not just a scientific development, that is a philosophical earthquake. And most people have no idea it happened. To understand the magnitude of what Voyager 2 crossed, you first need to understand what scientists believed they knew. The sun does not simply sit at the center of the solar system and glow. It breathes. Constantly and violently, it exhales. A torrent of charged particles, protons, electrons, magnetic fields, plasma, streaming outward in all directions at speeds exceeding 1 million miles per hour. This is the solar wind. It doesn't stop at Mars. It doesn't stop at Jupiter or Saturn or Neptune. It keeps going, pushing outward, expanding. The sun's magnetic influence like an enormous invisible bubble that swells far beyond the orbit of every planet in our solar system, extending well past Pluto, reaching distances that make the entire planetary neighborhood look like a speck of dust inside a cathedral. This bubble has a name. Scientists call it the heliosphere. And for most of the 20th century, the scientific community had a clear, coherent, mathematically supported picture of what its outer edge, the heliopause, would look like. The models predicted gradual transition, a gentle fading. Solar wind would slow over distance, weakening predictably, and then, at some critical point, it would yield to the pressure of the interstellar medium pushing inward from the galaxy. The boundary would be somewhat diffuse. The magnetic field would change direction as it crossed from solar space into galactic space. The temperature on the other side would be cooler, calmer, more settled. This was not a guess. This was decades of physics. This was the established picture. And this is where everything changes. When Voyager 1 crossed the heliopause in August 2012, becoming the first human-made object to enter interstellar space, it didn't send back confirmation of the established picture. It sent back something that deeply unsettled the scientific community. The boundary was sharp, not gradual, not diffuse. Sharp, like crossing a physical wall. The solar wind didn't fade. It vanished almost immediately. Galactic cosmic rays surged in a sudden leap that instruments registered clearly. And most bewilderingly, the magnetic field refused to change direction the way the models had demanded. According to every theoretical framework that existed at that moment, the magnetic field should have rotated as Voyager crossed from the heliosphere into interstellar space. It did not. It stubbornly, inexplicably maintained roughly the same orientation on both sides of the boundary. One scientist captured the moment perfectly when he said, and this quote deserves to be read slowly, "It just so happens that nature hasn't read the theorists' papers and didn't know that it was supposed to change the magnetic field direction. Read that again. The theorists' papers. The models that represented the best scientific understanding of our solar system's boundary were so precisely wrong that researchers had to resort to humor to process the embarrassment. But there was a problem with Voyager 1's data. Its plasma instrument, the device that directly measures charged particles and could definitively confirm the crossing, had stopped working back in 1980 after its encounter with Saturn. So while the other evidence was overwhelming, scientists couldn't be completely certain. They needed confirmation. They needed a second data point. They needed Voyager 2. Voyager 2 took a different path. While its twin had been flung northward and outward by the gravitational dynamics of the outer planets, Voyager 2 was sent southward toward a completely different part of the heliosphere. This was fortuitous in a way that the mission planners couldn't have anticipated. If the heliopause behaved differently at different points around the sun's bubble, having two probes crossing in different locations and at different times would reveal that variation, and it did, in ways that nobody was fully prepared for. On November 5th, 2018, Voyager 2 crossed the heliopause. Unlike its twin, it had a functioning plasma instrument, the same type of instrument that had fallen silent on Voyager 1 nearly 4 decades earlier. For the first time in history, humanity had a spacecraft with working sensors of every critical type crossing from the solar system into interstellar space. The data that came back triggered 5 separate research papers, published simultaneously in the journal Nature Astronomy. 5 papers from a single boundary crossing, because there was simply too much to report, too much that needed explaining, too many results that upended existing models. What most people are not seeing is how deeply strange the data actually was. Start with temperature. Scientists had modeled the interstellar medium, the thin, cold plasma that fills the space between stars, as having a temperature of roughly 15,000 to 30,000 Kelvin. That's extremely hot by human standards, but by interstellar standards it was the expected baseline. What Voyager 2 actually measured at the heliopause was a temperature between 30,000 and 50,000 Kelvin. Some measurements suggested figures even higher, touching 54,000 degrees Fahrenheit in some analyses. The boundary was not the temperature the models predicted. It was burning. There was a wall of fire sitting at the edge of our solar system, and the physics textbooks hadn't mentioned it. But here's where it gets worse. The temperature anomaly alone might have been explained away as a local compression effect, as the solar wind and interstellar medium collide and their energies pile up. But the magnetic field data told a different, deeper story. Voyager 2's magnetometer confirmed what Voyager 1 had hinted at. The magnetic field lines inside the heliosphere are parallel to the magnetic field lines in the region just outside it. This should not be possible according to the standard models of how the sun's magnetic influence interacts with the galactic magnetic field. The boundary should act as a separator, a zone of discontinuity where the two magnetic regimes meet and the field direction shifts. Instead, the fields align. 2 separate spacecraft crossing in different directions, years apart, both measured the same impossible result. According to informed sources in the heliophysics community, this finding has forced a fundamental reconsideration of how the sun's magnetic influence interacts with the broader galactic environment. The implications extend far beyond academic interest. If the solar magnetic field and the interstellar magnetic field are aligned across the heliopause rather than opposed, it raises questions about how effectively the heliosphere actually shields the inner solar system from galactic cosmic radiation. It raises questions about the shape of the heliosphere itself, whether the tidy, comet-like bubble shape that textbooks depict is actually accurate. And it raises questions about what is happening in the zone just beyond the heliopause, a region that Voyager has confirmed is not the calm, undisturbed interstellar medium that models predicted, but rather a turbulent, perturbed transitional zone that doesn't fit neatly into any existing theoretical framework. NASA's own Jet Propulsion Laboratory acknowledged this directly. Both Voyager 1 and Voyager 2, after crossing the heliopause, found themselves in what mission scientists described as a perturbed transitional region. Not the clean interstellar space that models had depicted, but something stranger, more layered and more dynamic than anyone had theorized. The boundary is not a line, it's a zone, and the zone behaves in ways that current physics can partially describe, but cannot yet fully explain. Think about what that means for everything else we think we know. If the boundary of our own solar system, the closest cosmic frontier we can actually reach with physical probes, is fundamentally different from what our best models predicted, what does that say about our models of things we cannot reach? What does it say about our understanding of other stellar systems, other heliospheres, other places in the galaxy where solar winds meet interstellar winds? The scientific community's confidence in its ability to model these environments has taken a significant and necessary hit, and the reverberations of that impact are still being felt today. There's another layer to this that the mainstream coverage largely missed. And when Voyager 2 crossed the heliopause, it also detected something that Voyager 1 had not found in the same measure. The heliosphere is leaky. Solar plasma from inside the heliosphere was observed trickling through the heliopause boundary and flowing approximately 100 million miles into interstellar space beyond it. Voyager 1, crossing at a different location, had detected almost none of this leakage. This means the heliopause is not uniform. It has porous regions and more solid regions. It breathes in different ways at different points of its surface, responding to the sun's activity and to the varying pressure of the interstellar medium pushing back, the protective bubble that shields our planet from the harshest. Radiation of deep space is not a clean, impermeable shield. It is a dynamic, variable, partially permeable membrane, and we had no idea until a 47-year-old spacecraft flew through it and told us. What most people are not seeing is the timing of these revelations and what they mean for current missions. In 2025, NASA launched the Interstellar Mapping and Acceleration Probe, known as IMAP, a mission that researchers have described as IBEX on steroids, equipped with higher resolution instruments designed to map the outer boundaries of the heliosphere in far greater detail than anything before it. IMAP is now positioned at what scientists call Lagrange Point 1, roughly 1 million miles toward the Sun from Earth, observing the heliosphere remotely while the Voyager probes observe it from the inside out. The combination of these two complementary observation strategies is beginning to produce a picture that is far more complex, far more dynamic, and far more unsettling than the field anticipated even a decade ago. The interstellar density beyond the heliopause, according to measurements taken across multiple years of Voyager observation, has continued to increase beyond the value recorded at the immediate boundary crossing. Nobody knows with certainty what this means. One interpretation is that interstellar material is accumulating near the heliopause the way snow piles up in front of a slow-moving plow. Pressure building, density rising, the interstellar medium pushing back against the heliosphere with growing force. If this is accurate, it suggests that the shape and size of the heliosphere itself may be slowly changing, responding to variations in both solar activity and the local interstellar environment. The heliosphere has expanded and contracted before, flexing with the Sun's 11-year activity cycle, and measurements near the heliopause have shown these fluctuations in real time. But the longer-term trend in interstellar density is a pattern that nobody has a clean model for yet. And this is where everything becomes genuinely alarming. The heliosphere is not simply an interesting cosmic structure. It is the shield that stands between the living biosphere of Earth and the full, unfiltered fury of galactic cosmic radiation. Galactic cosmic rays are high-energy particles accelerated by supernovae, by the violent deaths of stars scattered across the Milky Way, by processes occurring in distant, catastrophic stellar events. The heliosphere deflects and absorbs a significant fraction of this radiation. Without it, the particle bombardment reaching Earth's surface would be substantially higher. We are not talking about an abstract cosmic phenomenon. We are talking about a physical system that plays a measurable role in the habitability of our planet. If the heliosphere is more porous than models suggested, if its boundary is more variable, more dynamic, more responsive to changes in the interstellar environment, then its effectiveness as a radiation shield may also be more variable than we assumed. This has implications not just for astrophysics, but for astrobiology, for climate science, for our understanding of how life on Earth has been shaped by its position inside this solar bubble over geological timescales. During periods when the Sun moves through denser regions of the interstellar medium, and it does move, orbiting the center of the galaxy at roughly 140 miles per second, carrying its heliosphere with it, the boundary conditions would shift dramatically. There is evidence in Earth's geological record of periods of increased cosmic ray exposure coinciding with biological events whose causes have long been debated. Voyager's data gives this conversation a new and sharper edge. The real story is that Voyager 2 didn't just cross a boundary. It walked into a room that scientists had described in meticulous detail, and found that almost nothing in the room matched the description. The floor was in a different place. The temperature was wrong. The walls behaved differently than expected. There were doors nobody had drawn on the blueprints. And the instruments that were supposed to confirm the existing model instead came back with readings that demanded a new model, one that is still being written. As of January 2026, both Voyager spacecraft are more than 13 billion miles from Earth, operating in what NASA describes as survival mode. Their radioisotope thermoelectric generators, the nuclear power sources that have kept them running for nearly half a century, are waning. Mission teams have been methodically switching off non-critical instruments to conserve enough power to keep the essential science instruments alive for as long as possible. The first planned instrument shutdown for Voyager 2 is scheduled for 2026. Every day that either spacecraft continues to function is a gift Every packet of data that arrives is a transmission from the only outpost humanity has ever placed in true interstellar space. According to informed sources within the heliophysics community, the data flowing back from the Voyager probes during the current period of high solar activity, the Sun having been near its peak in the 11-year sunspot cycle around 2025, has been especially significant. Solar eruptions generate waves that propagate outward through the heliosphere, and when these waves reach the heliopause, they cause the electrons in the interstellar medium to oscillate, generating radio waves that the Voyager instruments can detect. These measurements allow scientists to calculate the electron density of the interstellar medium with remarkable precision for a region more than 13 billion miles away. And those density measurements have continued to produce surprises with values that keep pushing the limits of existing theoretical predictions. There's a detail in all of this that deserves more attention than it has received. When Voyager 2 crossed the termination shock, the inner boundary where the solar wind first begins to slow dramatically, years before reaching the heliopause, its plasma instrument detected something that nobody had expected: an unexpectedly strong magnetic field in the surrounding interstellar region, one powerful enough to physically distort and compress the heliosphere itself. The bubble the Sun creates is not the symmetric, or relatively spherical structure that standard models had depicted. The interstellar magnetic field was squashing it, deforming it, pushing it into an asymmetric shape whose exact contours are still being mapped and debated. The very geometry of our solar system's protective envelope